Welcome to this walkthrough of LeetCode problem number 1686, Stone Game 6. In this video, we'll explore the problem, break down its requirements, and analyze efficient approaches to solve it. Let's dive in. In this problem, Alice and Bob are playing a game with n stones, where each stone has a value assigned by both players. These values are provided in two arrays, Alice values and Bob values. The combined value of a stone is calculated as the sum of its value for Alice and its value for Bob. The game proceeds with Alice and Bob taking turns to pick stones, starting with Alice. On each turn, the player selects the stone with the highest total value, and in case of a tie, they can choose any stone among the tied ones. Each player then adds their respective assigned value for the picked stone to their score. The game continues until no stones are left, and the winner is determined based on the scores. If Alice has a higher score, the result is 1. If Bob has a higher score, the result is -1. If their scores are equal, the result is 0. The input to the problem consists of two integer arrays, Alice values and Bob values. Each array has a length of n, where n can range from 1 to 100,000. The values in these arrays are non-negative integers between 0 and 100. The output is a single integer, which can be 1, -1, or 0, indicating whether Alice wins, Bob wins, or if the game ends in a tie. For example, consider the case where Alice values is 1, 3, and Bob values is 2, 1. The output is 1, which means Alice wins the game. Here's why Alice wins in the example. The total value of the stones is calculated as 3, 4. Alice goes first and selects the stone with the highest total value, which is 4, corresponding to the second stone. She adds her assigned value for this stone, which is 3, to her score. Bob then picks the remaining stone with a total value of 3, adding his assigned value, 2, to his score. By the end of the game, both players have scores of 3, but since Alice went first, she is declared the winner. Now, consider another example where Alice values is 1, 2, and Bob values is 3, 1. In this case, the total values are 4, 3. Alice picks the stone with total value 4, adding 1 to her score, while Bob picks the stone with total value 3, adding 3 to his score. The final scores are Alice with 1 and Bob with 4, resulting in Bob being the winner. Let's examine another example where Alice values is 2, 4, 3, and Bob values is 1, 6, 7. The total values are 3, 10, 10. Alice starts by picking the stone with the highest total value, which is 10 at index 1. She adds her assigned value, 4, to her score, while Bob adds his assigned value, 6, to his score. Bob then picks the remaining stone with a total value of 10 at index 2, adding 7 to his score. Finally, Alice picks the last stone with a total value of 3, adding 2 to her score. The final scores are Alice with 6 and Bob with 13, so Bob wins the game, and the output is -1. The constraints of this problem require an efficient solution. The number of stones, n, can be as large as 100,000, which means that operations like sorting and comparisons need to be optimized. The values assigned to the stones, ranging from 0 to 100, are relatively small, so calculations involving these values are computationally cheap. The key strategy for both players is to always pick the stone with the highest total value, ensuring they maximize their scores. For edge cases, when there's only one stone with values 0 for both players, the result is a tie since both scores will be 0. If all stones have equal values, both players will end up with the same score. For large inputs, the solution must handle arrays of up to 100,000 elements efficiently to avoid exceeding time limits. To start, let's consider the brute force approach to solving this problem. The idea here is to simulate every possible sequence of moves by Alice and Bob. For each turn, we would calculate the scores for both players based on their respective preferences, and evaluate all possible sequences of stone picks to identify the one that maximizes the score difference. While this approach is conceptually straightforward, the implementation involves iterating through all permutations of the stones, which leads to a time complexity of factorial growth, or O(n). This makes it computationally infeasible for larger inputs, as the number of permutations becomes astronomically large very quickly. Although simple in theory, the brute force approach is impractical for solving this problem efficiently given the constraints of real-world scenarios. Now, let's examine a more refined method, the greedy approach with priority. The intuition here is that each stone has a value for Alice and Bob, represented by Alice values, I, and Bob values, I. Combining these, we can calculate the total value of each stone as total value, I, equals Alice values, I, plus Bob values, I. Stones with higher total values are inherently more impactful to the overall game, so prioritizing them is key. To implement this, we compute the total value for each stone and then sort the stones in descending order of their total value. Once sorted, the game simulation begins by having Alice and Bob alternate turns, each picking the highest value remaining stone from the sorted list and adding its respective value to their score. This approach reduces the time complexity to O, n log n, due to the sorting step. However, it assumes that the total value is the sole determinant of a stone's importance, which might not always capture the nuances of the game, especially in certain edge cases where player-specific priorities differ significantly. Building on this, we arrive at the optimized greedy approach, which incorporates additional strategic insights. First, it is essential to recognize that Alice and Bob are not just maximizing their scores independently, they are also indirectly minimizing each other's scores. This means that evaluating stones solely based on their total value may not be sufficient. Instead, we factor in the difference between the importance of a stone to Alice and Bob. Specifically, a stone with a high value for Alice and a low value for Bob is more advantageous to Alice than one with equal values for both players. To implement this, we calculate the relative importance of each stone as Alice values, I, Bob values, I. Using this metric, we can prioritize stones using either a max heap or by sorting them in descending order of relative importance. During the game, Alice picks the stone with the highest priority on her turn, maximizing her score while minimizing Bob's potential gain, and Bob does the same on his turn. This method ensures that each player's choices are strategically aligned with their goal of maximizing their advantage. At the end of the simulation, the final scores are compared to determine the winner. In terms of efficiency, the optimized greedy approach is a significant improvement over the brute force method. Its time complexity is O, n log n, stemming from sorting or heap operations, as opposed to the factorial growth of O, n, in the brute force approach. This makes it far more practical for larger inputs. In terms of effectiveness, prioritizing stones based on their relative importance ensures that both players make optimal decisions within the constraints of the greedy strategy. Additionally, the implementation is relatively simple, avoiding excessive computations while still delivering strong results. However, it's worth noting that the greedy approach assumes that each choice is made independently of future decisions, meaning it does not account for long-term dependencies between moves. While a more global strategy might offer slight improvements in rare cases, it would come at the cost of increased computational complexity. Overall, the optimized greedy approach strikes a balance between efficiency and strategic effectiveness, making it a highly suitable solution for Stone Game 6 under typical constraints. To dive into the algorithm, we start by defining the problem clearly. In this two-player game, Alice and Bob take turns choosing elements from a sequence of integers, aiming to maximize their scores. Alice always goes first, and after all elements are chosen, the goal is to compute the maximum possible score difference between Alice and Bob. To analyze this, we use a brute force approach that simulates all possible sequences of choices. First, we define our problem variables. The array of integers ARR represents the sequence, and the size of this array is denoted as n. Alice and Bob alternate turns, with Alice's score being the sum of the elements she picks and Bob's score being the sum of the elements he picks. The objective is to evaluate every possible sequence of moves to determine the maximum difference, Alice_score, Bob_score. To achieve this, we use a recursive simulation to explore all combinations of choices and calculate the resulting scores. This setup ensures that we are thorough in analyzing all possible outcomes of the game. To implement the recursive simulation, we define a function DFS, start, end, is Alice's turn, to represent the decision-making process. The parameters start and end represent the current bounds of the array, while the boolean is Alice's turn indicates whose turn it is to play. The base case occurs when start exceeds end, meaning the array is exhausted, and no further scores can be added, so the function simply returns 0. For the recursive case, the logic depends on whose turn it is. If it is Alice's turn, she will aim to maximize the score, so the function returns the maximum of two choices, either picking the leftmost element at ARR start or the rightmost element at ARR end. Conversely, if it is Bob's turn, his goal is to minimize Alice's score, which is equivalent to maximizing his own advantage. Thus, the function returns the minimum of the two choices, adjusted for the score difference. Finally, the recursive process is initialized by calling DFS 0 and 1 true, which starts the simulation with Alice's turn and the full bounds of the array. The return value of this function gives us the maximum score difference achievable. This recursive approach provides several key insights into the problem. First, every player at each step faces a binary decision to pick either the leftmost or rightmost element of the current array. This binary decision-making process is fundamental to the recursive simulation, allowing us to explore all possible sequences of moves. The algorithm relies on game theory logic, where Alice always tries to maximize her score while Bob tries to minimize Alice's score, which effectively means maximizing his own. The score difference is adjusted dynamically depending on whose turn it is, ensuring that the recursive function correctly models the competition. The recursion stack plays a critical role here, storing the current bounds of the array and the turn information. This stack grows proportionally to the size of the array, making the space complexity of the recursive approach directly tied to the input size. Additionally, the input array itself remains unchanged and is simply referenced during the recursive calls. These insights highlight how the algorithm systematically explores all possible outcomes using recursion. Now, let's analyze the key operations and the complexity of this approach. At each step of the recursion, two recursive calls are made, one for picking the leftmost element and one for picking the rightmost element. This results in a total of O2 to the power of n recursive calls, where n is the size of the array, as we explore all possible subarray states. The base case, which occurs when the array is exhausted, has a constant time complexity of O1. The space complexity is determined by the recursion stack, which requires O(n) space due to the depth of the recursion. To optimize this brute force approach, we can use memoization. By caching the results of previously computed states in a 3D array dp, start end is Alice's turn, we avoid redundant calculations, reducing the time complexity to O(n squared). Additionally, we can further optimize the solution by converting the recursive approach into an iterative dynamic programming table. This eliminates the overhead of recursion while still achieving the same results, making the algorithm more efficient and scalable. Finally, let's consider some edge cases to ensure the algorithm handles all scenarios effectively. If the array has only one element, there is only one possible move, Alice picks the element, and the score difference equals the value of that element. For an array where all elements are equal, the score difference will always be 0, as both players will accumulate the same total score regardless of their choices. In cases where the array alternates between large and small values, the algorithm ensures that optimal decisions are made at each step. Alice and Bob will strategically pick elements to either maximize or minimize the score difference, with the recursive simulation or dynamic programming approach capturing these decisions accurately. These edge cases demonstrate the robustness of the algorithm, as it accounts for a variety of input scenarios and ensures the correct result is computed in all cases. This implementation solves LeetCode problem number 1686 Stone Game 6 using a greedy approach. The problem requires simulating a two-player game where Alice and Bob alternately pick stones to maximize their respective scores. ###explanation. 1. Combine Alice's and Bob's values. We combine the values from both players into a single list of tuples, where each tuple contains the total value, Alice's value plus Bob's value, Alice's value, and Bob's value for a particular stone. 2. Sort the combined list. The list is sorted in descending order by the total value, sum of Alice's and Bob's values. This ensures that the most important stones, those that maximize the combined utility, are considered first. 3. Alternate turns. Iterate through the sorted list. On Alice's turn, even indices, add Alice's value for the chosen stone to her score. On Bob's turn, odd indices, add Bob's value for the chosen stone to his score. 4. Calculate the result. After all stones have been chosen, compare Alice's and Bob's scores. Return 1 if Alice's score is higher, -1 if Bob's score is higher, and 0 if their scores are equal. ### complexity. Sorting the combined list takes O, n log n, where n is the number of stones. Iterating through the list is O, n. Thus, the overall time complexity is O, n log n. This approach is efficient and ensures that both players maximize their scores based on the game's rules. Here, we start by importing the necessary Java utilities and defining our solution class. Inside the Stone Game VI method, the input consists of two arrays, Alice values and Bob values, which represent the values each player assigns to the stones. The first step is to create a list called combine that stores tuples containing three elements: the sum of Alice's and Bob's values for each stone, Alice's value for that stone, and Bob's value. This allows us to consider both players' perspectives while sorting the stones. Next, we sort this list in descending order based on the combined value, ensuring that the stones with the highest shared importance are considered first. After sorting, we initialize two variables, Alice score and Bob score, to track the points each player accumulates. The game proceeds in alternating turns, starting with Alice. On Alice's turn, she adds her value for the selected stone to her score, while on Bob's turn, he adds his value to his score. This alternation continues until all stones are picked. Finally, after all the stones have been distributed, we compare the total scores of Alice and Bob. If Alice's score is greater than Bob's, we return 1 to indicate that Alice wins. If Bob's score is greater, we return -1 to signify Bob's victory. If both scores are equal, the game ends in a tie, and we return 0. This logic ensures that the result accurately reflects the outcome of the game based on the rules and the player's values. By structuring the solution in this way, we ensure that the implementation is both efficient and easy to follow. To solve this problem, we start by combining Alice's and Bob's values into a single list of tuples. Each tuple consists of three elements: the sum of their values, Alice's value, and Bob's value. For the first example, where Alice's values are 1, 3, and Bob's values are 2, 1, the combined list becomes 3, 1, 2, 4, 3, 1. This step helps us evaluate the overall importance of each stone. Next, we sort this combined list in descending order based on the sum, which prioritizes stones with the highest total value. After sorting, the list becomes 4, 3, 1, 3, 1, 2. Now, we initialize the scores for Alice and Bob as 0, and we alternate turns selecting stones. On the first turn, Alice picks the stone with values 4, 3, 1, so she adds her value 3 to her score, resulting in Alice _score equals 3. On the second turn, Bob selects the next stone, 3, 1, 2, and adds his value 2 to his score, making Bob _score equals 2. After all stones are picked, we compare the scores. Alice has a score of 3, while Bob has a score of 2. Since Alice's score is higher, she wins, and we return 1. For the second example, where Alice's values are 1, 2, 3, and Bob's values are 3, 2, 1, we follow the same process. First, we combine their values into tuples, resulting in 4, 1, 3, 4, 2, 2, 4, 3, 1. Each tuple reflects the sum of the values, along with Alice's and Bob's specific contributions. Then, we sort this list in descending order by the sum, which results in 4, 3, 1, 4, 2, 2, 4, 1, 3. This ensures that the stones with the highest total value are considered first during the alternating turns. Now, we reset both scores to 0 and begin alternating turns. On the first turn, Alice selects the stone, 4, 3, 1, and adds her value, 3, to her score, making Alice _score equals 3. Next, it's Bob's turn, and he picks the stone, 4, 2, 2, adding his value, 2, to his score, so Bob _score equals 2. Finally, Alice takes the last stone, 4, 1, 3, adding her value, 1, to her score, resulting in Alice _score equals 4. Comparing the scores, we see that Alice has 4 while Bob has 2. Since Alice has the higher score, she wins again, and the function returns 1. For the third example, Alice and Bob's values are both 1, 1. Combining their values into tuples gives 2, 1, 1, 2, 1, 1. Since all the sums are identical, the list is already sorted. We initialize the scores to 0 and alternate turns. During the first turn, Alice selects the first stone, 2, 1, 1, adding her value, 1, to her score, so Alice underscore score equals 1. Bob then takes the second stone, 2, 1, 1, adding his value, 1, to his score, making Bob underscore score equals 1. After all turns are complete, both Alice and Bob have equal scores of 1. When Alice and Bob's scores are tied, the game ends in a draw, so the function returns 0. This demonstrates how the solution handles cases where the player's scores are equal, reflecting a fair outcome based on the alternating selection process. The final output for this example is 0. The time complexity of this solution is determined by three main operations. First, we combine Alice's and Bob's values into tuples using the zip function. This operation iterates over both input arrays, Alice values and Bob values, simultaneously, creating a list of tuples in the format a plus b, a, b. Since we're iterating over arrays of length n, this step takes n time. Next, we sort the combined list based on the first element of each tuple, which represents the sum of Alice's and Bob's values. Sorting in Python uses timsort, a highly efficient sorting algorithm with a time complexity of n*log n for a list of size n. Finally, we iterate over the sorted list to calculate Alice's and Bob's scores. This involves a single traversal of the list, which is another n operation. Combining these steps, the sorting operation dominates the overall time complexity, making it n*log n. Now let's look at the space complexity of the solution, which is determined by the auxiliary data structures we use. The most significant factor is the combined list of tuples, where each tuple contains three integers, the sum of Alice's and Bob's values, and their individual values. Since this list has n tuples, the space required is n. Additionally, the Python sort function operates in place, meaning it doesn't require extra space for sorting, so this step contributes only 1 space overhead. Finally, the variables we use, such as Alice underscore score, Bob underscore score, and the loop iterator, require constant space, or 1. When we consider all these components, the total space complexity is dominated by the combined list, leading to an overall space complexity of n. Let's compare this optimized approach with a brute force or naive approach. In a naive solution, we would explore all possible permutations of the stones to determine the optimal strategy for Alice and Bob. This involves generating all permutations of the indices, which has a factorial time complexity of n. Such an approach is computationally infeasible for larger inputs due to the exponential growth of factorial functions. In contrast, the optimized approach sorts the stones based on their combined score, a plus b, and alternates turns between Alice and Bob to simulate the game efficiently. This eliminates the need to exhaustively explore all permutations and reduces the time complexity to n*log n, making it practical for larger datasets. By focusing on sorting and straightforward iteration, this method significantly improves performance while maintaining the correctness of the solution. The time complexity of the solution remains n*log n in all scenarios, best, average, and worst case, because the sorting step is always the most computationally intensive operation, and it depends only on the size of the input, not on the specific values of the elements. To summarize the mathematical proof, the time complexity includes n for combining values, n*log n for sorting, and another n for iterating through the sorted list to calculate scores. Adding these together, we get n plus n*log n plus n, which simplifies to n*log n, since the sorting step dominates. The space complexity is n, as it is determined by the combined list of tuples. Overall, this solution is highly efficient, with the sorting operation being the key contributor to the computational cost. Compared to the brute force approach with its factorial time complexity, this optimized solution is significantly faster and scalable for larger inputs. One of the most common mistakes in solving problems like Stone Game 6 is overlooking edge cases. For instance, input arrays might be empty or contain only one element. Extreme values, such as very large or very small numbers, can also cause unexpected behavior. Testing these edge cases explicitly ensures your solution is robust. Another frequent issue is rushing through the brute force implementation. Many candidates fail to properly iterate through all combinations or neglect to reset variables correctly, which leads to incorrect results. Always verify that your brute force solution is correct before attempting optimization. Additionally, recursion without memoization can be a major pitfall. Solving subproblems repeatedly without caching results can cause your solution to balloon into exponential time complexity, which is highly inefficient. To avoid this, implement memoization to store and reuse intermediate results. Lastly, misjudging time complexity can be problematic. Using an n² approach for large input sizes, such as n equals 10 to the power of 5, will likely result in time limit exceeded errors. Always analyze the constraints and adapt your solution accordingly. Finally, never assume your first implementation is accurate. Validate outputs against known test cases and use debugging tools to spot potential issues early on. In an interview setting, it's important to communicate your thought process clearly. Start by breaking down the problem and presenting a brute force solution to demonstrate your understanding, then transition to optimized approaches. Recognizing common patterns, such as dynamic programming, greedy algorithms, or divide and conquer, can significantly speed up your problem solving. Practice identifying these patterns across various problems. Interviewers also evaluate your ability to balance time and space complexity, so be prepared to discuss trade-offs between different approaches. For example, you might choose dynamic programming to eliminate redundant calculations, even if it uses more memory. Explaining such decisions shows a deep understanding of the problem. Additionally, asking clarifying questions at the start ensures you fully grasp the problem requirements and avoids wasting time on incorrect assumptions. This step is critical for aligning your solution with what the interviewer expects. To deepen your understanding of problems like Stone Game 6, consider exploring related challenges. For instance, LeetCode 198, House Robber, is a classic dynamic programming problem that focuses on maximizing sums while skipping adjacent elements, a concept that can appear in many variations. LeetCode 1143, Longest Common Subsequence, introduces 2D dynamic programming, which is useful for solving problems involving sequences or grids. LeetCode 53, Maximum Subarray, provides an excellent foundation in dynamic programming combined with greedy strategies, particularly through Cadon's algorithm. Lastly, LeetCode 494, Target Sum, demonstrates how to use dynamic programming to work with subsets, which is a valuable skill for partition-based problems. Working through these challenges will strengthen your ability to identify and apply the right techniques in different scenarios. When tackling problems, alternative approaches can often provide more elegant or efficient solutions. Dynamic programming is a powerful method for problems with optimal substructure, but it's essential to optimize space usage for large inputs to maintain efficiency. Greedy algorithms, on the other hand, can simplify problems by making locally optimal choices at each step. However, you must ensure the problem satisfies the greedy choice property before relying on such methods. Divide and conquer is another strategy that works well for naturally partitioned problems, such as those involving binary search. While efficient, merging results in divide and conquer algorithms can sometimes be tricky and requires careful handling. Finally, consider the trade-offs between iterative and recursive solutions. Iterative approaches tend to be more space efficient, avoiding issues like stack overflow, but recursive methods can be cleaner and more intuitive, especially for tree-like structures. Mastering these techniques will equip you to solve a wide range of problems with confidence and flexibility. That brings us to the end of this session on Stone Game 6. We've covered the problem, analyzed various approaches, and learned key techniques to tackle similar challenges. Thank you for watching, and don't forget to like and subscribe for more content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!